In this video, we're going to talk about simple linear regression and polynomial regression. This is going to be the most important video, theoretically speaking, of the entire modeling series, so I would encourage you to maybe watch it quickly once and then revisit it as you need to, because especially for regression topics, this is the most important video. So let's get started. To begin, we need to talk about some regression terminology. Simple linear regression, or SLR, is a simple regression model where f of x, the relationship between x and y, is described by a line. Beta naught and beta 1 are unknown, those are the parameters, and they must be determined from the data itself. This problem is called estimation in statistics, and in machine learning it's called learning. When you're actually ready to compute the estimates, so not thinking about how you're going to compute them from a theoretical perspective, but when you're actually ready to compute them, we call that process fitting, or in machine learning, training. The estimates that you derive for the unknown quantities beta naught and beta 1 are denoted beta naught and beta 1 with this little triangular circumflex above it. We call those hats. So we say beta naught hat and beta 1 hat. Sometimes that's a little challenging to typeset. So if you find it challenging to typeset, just write it B naught and B1. Collectively, we'll denote these bold-faced beta hat or bold-faced beta, and they mean exactly the same thing. They're just the estimates for the unknown regression parameters beta naught and beta 1. The function itself is called the regression line, and sometimes we'll write that with a hat as well. So f hat of x is equal to the line, but the line is using the estimated regression coefficients. That's the beta naught and beta 1 hat. Let's take a look at the picture. Again, we have the beta plane and the xy plane, and now I've added to the xy plane the points that we want to run a line through. And when we're looking for a good line, different lines will kind of look better or worse. For example, if I pick this point in the beta plane, it corresponds to that line, and that line looks pretty decent. However, I can choose a different line, which is a different point in the beta plane, and yet still corresponds to a roughly reasonable line. Obviously, there are also a lot of bad lines, though. For example, this blue point corresponds to a line which clearly doesn't fit the data very well. In general, there's going to be some kind of rough region where all of the lines in that region, in the beta plane, are about as good as any of the others. This is a statistical topic that we don't really dig into deeply, but is really important if you move on in statistics. Now, let's suppose for a moment that we actually have a best fitted line in hand. So we call that, remember, f hat of x. Predicting a y for a new x is a really easy thing to do. Why is that? Well, because the y hat value, that's going to be the predicted value for the new x value, is just going to be created by applying f hat to the new x value that we have. And since we have a line, that's just beta naught hat plus beta 1 x new. Let's look at the picture. So here's the data. Here's my best fit line. So supposing that I have such a thing, we haven't yet figured out how we're going to create that. If I have a new x value, like right here, I can predict the y value for that new x value simply by finding the y value associated with that point on the line. So again, f hat of x new is going to give me the predicted value. We usually call this y hat. Now, let's go back to that question of what is the best fit line. To figure out what we mean by best fit line, we really need to have a quantitative measure of how bad a line is. I usually like to refer to this as badness. So we're going to have a badness measure, and the idea is that a badness of 0 is going to be a perfect line. It's going to go through all of the points, and otherwise, the bigger the badness measure, the worse the line is. So how do we actually kind of figure out what this thing is? So let's suppose that we have a candidate line. The candidate line looks like this. So that line looks maybe reasonable, maybe not so reasonable, but it's definitely a line that's in the running. How do I measure how bad it is? The basic idea here is that the best line should predict well for all points that you already know the y values to. So this goes back to that idea of being supervised machine learning. So for example, here's a point xi, yi, and if I use the line to predict what the y value would have been for that point, let's suppose that I forget what the y value is, or I pretend like I forget what it is, and I use the line to predict what the y value would be, I would call that y hat I. I just use the line, I plug in xi for x, and I get my y hat I value. We usually refer to this as the predicted or the fitted value for xi. Now here's the thing, I've actually observed the real value of yi. So I know what the predicted value actually should be. The difference here is yi minus y hat I. That's kind of like the error associated with my prediction. That's how much I missed by. And we call this in statistics EI, or the ith residual. That's an important term that we're going to need to remember as we move on, is residuals. It's the kind of leftover stuff after the model has explained away everything that it knows about. It's how much the model missed by. Of course, I can compute residuals for every single point in my data set, and some of those are going to fall above the line and some are going to fall below the line. So some of the residuals are going to be positive and some of them are going to be negative. Now remember what I'm trying to look for here. I'm looking for some kind of quantitative measure of the badness of the line. The measure that we're going to use, the overall badness measure of the line, is going to be the sum of the squared residuals, or the residual sums of squares, and that is denoted RSS. This is a really important quantity in modeling. And of course, it depends on the line that you choose. Different lines will have better RSS values or worse RSS values. It just kind of depends on which line you choose. In other words, the residual sums of squares is itself a function of the line, and we know that every line corresponds to a pair of numbers, beta naught, beta 1. So I could write it like this. The residual sums of squares for the line called beta naught, beta 1 is equal to the sum of the squared residuals. If I expand that, that's equal to the sum of yi minus y hat I squared. And if I expand that further, the y hat I is actually just plugging in xi to the candidate line that we have, which depends on beta naught, beta 1. So this is the formula that we have for the residuals. In this formula, of course, you know what xi and yi are because you have the data. And you can plug in beta naught and beta 1 because those are just different candidate lines. And the idea is that you want to minimize that badness measure. The best line is going to be the one that minimizes the residual sums of squares. Now, as a mathematical fact, there's actually a single unique line that minimizes the residual sums of squares. So in that sense, there is a best fit line. It's actually easy to prove this with calculus or geometry, and in mathematics, you'll encounter this in a class called linear algebra, which is absolutely foundational in statistical modeling. It's a class that you would take after calculus 2. Now, there are actually explicit formulas that exist for beta naught hat and beta 1 hat in terms of the xi's and the yi's, but in general, they're not very helpful. They can help you understand kind of some statistical properties of beta naught hat and beta 1 hat, but otherwise, they're not very useful and we almost never use them in practice. The good news is that computers can compute beta naught hat and beta 1 hat very, very easily. This computation is a very easy computation to do, even if you have very, very large data sets. Now, the RSS criterion, the residual sum of squares criterion, is usually referred to as least squares. So the best fit line is often called the least squares line. And this is something that was discovered by the great German mathematician Carl Friedrich Gauss while he was working on some astronomical data. So there's some great math history that comes into play here as well. Now that we know what the best fit line is, it helps to talk about various aspects of things related to it. So let's start with interpretation. Beta naught is in the same units of y, so it's very easy to interpret. It tells us the value of y when x is equal to 0, but that may be meaningless in your particular situation. For example, a person's weight when their height is 0 is kind of a meaningless quantity. As a second example, the pH when the dissolved oxygen is 0 is a specific quantity. That would be the beta naught, and that would be kind of a baseline. The reverse, of course, is meaningless. We wouldn't ask what the dissolved oxygen content is when the pH is 0 because a pH of 0 is not a valid pH level. In terms of beta 1 is interpreted in units y per unit x, just like in lines ordinarily. It tells us the expected change in y when x is increased by 1 unit. For example, for every additional inch of height, we expect an increase in weight by whatever beta 1 is. Or, for every additional milligram per liter dissolved oxygen, we expect an increase in pH of whatever beta 1 is. Be careful not to interpret this causally. Underlying factors may motivate the relationship that you're seeing. So it's difficult to say that if we manipulate the x variable by a certain amount, the y variable will certainly change by a corresponding amount. We expect that to happen, but we need to be careful not to interpret things causally. Another aspect of this is that the causal arrow may be hard to determine. In other words, does x cause y or does y cause x? In the example of water, does the pH affect the dissolved oxygen content or does the dissolved oxygen content affect the pH? It's probably actually the latter. There are many regression quantities that we're going to want to know about. The first is the root mean squared error, or the RMSE. The residual sum of squares of the best fit line is close to a measure of dispersion, right? It's a sum of squared errors. If we divide that by n, we get something called the mean squared error, and that's a kind of estimate of the variance. The root mean squared error is the square root of the mean squared error. It's an estimate of the standard deviation, and it's going to be in the same units as the response y. It measures the lack of fit of the line. So a larger RMSE, a larger root mean squared error, means the line doesn't fit as well, or that our ability to predict y given a particular x is not as good because there's a large amount of noise associated with it. Another quantity that you'll hear referred to a lot is the correlation coefficient. It's denoted lowercase r. The correlation coefficient is directly related to the slope coefficient beta 1, and here's the relationship. The correlation coefficient is equal to the estimated slope times the standard deviation of the x divided by the standard deviation of the y's. So the correlation coefficient is simply proportional to that slope term, and it's going to have the same sign since both sx and sy are positive. So it's a scaled version of the slope of the line, It must be between -1 and 1. That's a more challenging fact to prove, but it's nevertheless always true. If it's positive, that means that the slope term is positive. So there's a positive relationship between x and y, and if it's negative, it means that there's a negative relationship between x and y. And be careful here because the correlation coefficient only measures linear relationships. There's a whole bunch of examples where there's strong patterns that you see in the data that are not linear patterns and for which the correlation coefficient gives a counterintuitive measurement like 0. For example, in the bottom row here, we see a whole bunch of data sets where the correlation coefficient is 0. Nevertheless, there are very strong patterns that you see in the data. So just because a correlation coefficient is 0 does not mean the data are unrelated. It means that there's not a linear association between those values. Now, just like we can do linear regression, we can also fit polynomials to data sets as well. For example, we could fit a parabola to a data set, or we could fit a cubic. This can be useful in various circumstances. Be careful because the interpretations are more challenging. The interpretation is no longer global. The change in y per unit change in x depends on what x is. For example, going from x equals 1 to x equals 2 is going to be different than going from x equals 11 to x equals 12, even though there's 1 unit difference in both circumstances. So interpretations are no longer global. Now, local interpretations are simple mathematically, but they're kind of complicated to put in a layperson's terms. So just in general, interpretation gets more challenging. Nonlinear functional form. In almost every case, f of x will not actually be a line, and that was the example that we began with, where f of x here is this kind of wiggly curve. Obviously, it's not a line. Nevertheless, assuming that f of x is a line can be a helpful thing to do. This goes back to our quote from Box. Here would be an example of a best fit line, and f hat of x is still telling us the general trend of the relationship, that it's positive, and it can tell us aspects of the error as well. Now, what if f of x isn't a line or a polynomial? So this is continuing this discussion on a nonlinear functional form. For example, let's say that you have a data set that looks like this. In general, we'll do transformations of x and y to try to convert the problem into a linear problem. Before I illustrate this for you, I'll say, be careful, there are many statistical pitfalls that you can run into here, so in general it's a good idea to get help or to take a course in regression before you start really playing around with nonlinear functional forms. But this kind of stuff is done fairly routinely. In statistical learning, transformations of x are usually referred to as feature engineering, and they very often traditionally use domain expertise, although nowadays you'll see artificial neural networks try to learn features from the data itself without input from an expert. In the case that we're looking at, a transformation like taking the log of y may be a sensible thing to do. It looks like there's exponential growth in the y given the x, so if we take the logarithm of the y, it'll probably flatten out as a line. Now, in practice, there would be variability considerations, but this is the basic idea. Residual plots are helpful diagnostic tools for nonlinearity. So how do you even know that you have nonlinearity in the first place? A residual plot is a scatter plot of x on the x-axis and the residuals on the y-axis. An ideal model has no discernible pattern when you do this. So here's the original data with the residuals in red and green. Here is a residual plot where on the x-axis you have x and on the y-axis you have y minus y hat. In general, we should see no discernible pattern. There should not be some kind of trend that we see in this residual plot on the right. Lastly, some things to look for. When you're analyzing relationships, you should ask yourself several questions. First, what's the general pattern or trend of the relationship that you see? Are there exceptions to that general pattern? How strong is the relationship? Is the RMSE very small or is it very large? Do you suspect if somebody gives you the predictors that you will be able to predict the response with a high degree of accuracy? Could the observed relationship be due to chance? This may be a sample size consideration. If you have a small sample size, it's always difficult to say things with a high degree of certainty. But even when you have a large sample size, the observed relationship may be due to chance. Are there other relevant factors that are not in the model? This is usually in terms of other variables that are not in the model that should be considered as relevant towards the response, but aren't there. That can confuse or confound the interpretation that you derive from your model. Lastly, are there outliers that influence the model? Are there specific values that are moving the regression line quite a bit? Lastly, these are often assessed graphically. When you're actually doing modeling, your graphical tools are complementary to your modeling tools. They don't just go away.